Hello, am I audible?
Yes, sir.
Okay. Okay, let's start then. Whoever will be joining later, they will continue from that, and everyone can access this video in YouTube. I'll be sharing the link and also notes, everything, and everyone can access it. So, and basically, Viswajit Naik, and I'm a PMRF scholar, first year, and I'm currently studying in IIT Kharagpur. So I'm doing this material characterization. Uh, I'm helping Professor S. Sankaran. He's from IIT Madras in this course material characterization. And in first week, what he has done, he has given a fundamental of optics, where he has talked about properties of light, image formation, magnification, resolution, depth of field, depth of focus. So from first of all, I will review whatever is done in the first week. Then I will go through the questions. So first, he started with light. Like, he defined what is light. He described about the dual nature of light, and he has explained like when light can be used as particle as well as wave. Like, while detection, this light can be the particle nature of light is exhibited while we are considering the detection part, and when we are considering the propagation part, the nature of light is expected to be as a wave. So then he moved forward to explaining the quality of light, where he explained about monochromatic light, polychromatic light, linearly polarized light, non-polarized light, current light, non-current light, collimated and divergent light. So, in explaining, so first explained about monochromatic light, that is, all the waves which were considered are having same phase, where they are basically following the same trend. But in polychromatic, these are random. They can have any phases, any direction, and anything. But while considering okay, then first of all, monochromatic, polychromatic, then explain about linearly polarized light, then non-polarized, then coherent, then non-coherent, then collimated, and divergent. So as I've already explained, monochromatic and polychromatic light, the linear polarized light, the electromagnetic waves are only uh, having polarization in one direction only in linearly polarized light. In non-polarized light, it can have it has random direction. The polarization have random direction, and for coherent light, they have same phases. If the waves are considered, then they will be in same phase, but in non-coherent light they have different phase. And collimated one, all the waves have same direction, but in divergent, as the name suggests, the direction are diverging, maybe outward or inward, anything. So then next he explained about the brightness and intensity. uh, Brightness intensity is basically explained as rate of flow of light, energy per unit area per unit time. So its unit can be given by watt per meter square. Am I audible, right?
Yeah, we can hear you.
Clearly, loud and clear. Am I loud and clear? Okay, okay, thank you. So for brightness, like brightness is described as how many particle source can emit per unit area per solid angle per second particle per charge flux density per unit solid angle. So its unit is defined as area per meter square into steradian. So then he moved to Snell's law, where we all know, like, it is given by sine I by sine R n2 upon n1 by b1. So in sine, here I is basically incident ray, angle of the incident ray. R is reflect the ray which is reflecting at an angle R. Then n2 and n1 are basically a refractive index of two mediums, and v1 and v2 are a velocity at different mediums. So then he described about the lens and rules. So for lenses, first, so it's common formula which we know with the focus and distance. U is basically the distance from the lens, object distance, and U V is the image distance. Then magnification is given as V by U. For real image, so for new guys, what I'm doing is I'm basically recapitulating what has been done in week 1, and later I will be solving the problems which no, the practice ones, not the given assignment one. So in week 1, basically optical properties of microscope are focused, and so here I'm explaining the lens formula where the objective lens, what will be the magnification for the objective lens and the eyepiece lens. So for as we already know, like the relation between the BE by FB plus 1. So then the total magnification is basically product of the objective magnification to that of eyepiece. Then after that he explained a little bit about diffraction and interference, how diffraction and interference are basically same things. Like one diffraction, one is scattering is happening at the edge of a lens, and interference is basically summation of the uh, the summation of the waves which are coming. So these two phenomena, diffraction and interference, are basically a phenomena of scattering. So as we all know, we use this word scattering very casually, but yeah, there are a lot of yeah, it has a lot of, I would say, uh, uh, sub subsections. Like as we say, one have superset, and it has a small subset of it. So diffraction and interference are subset of this scattering. So next is Abbe's criterion. What is this? For lens to form an image, at least two
Hello,
diffracted.
Mr. Yeah, I'm saying, could you please draw this, what kind of waves are there for constructive interference and destructive interference?
Yeah,
Because you
sure.
told that in the class, so I'm not able to understand that.
Okay. Mm, for constructive interference, like let's say two waves are there. Okay. So here I'm basically giving them same phases, so it will be easy to add up. So when they will add up, the wave, we can assign it with any equation, right? So for simplest equation, we may say um, some amplitude and I'm not writing in terms of exponential, I'm writing in terms of sine and cos. So sine some omega x. Okay, so if this two waves will be given, so this will add up and sorry, this will add up and the amplitude of this thing will add up, because there is no phase difference as of now. I have given in this two equation. Okay, so this is basically what is constructive interferences. And for destructive interference, this to have opposite phases, so when they will add up, then it's basically nullified. Either if the magnitude of this uh, wave, this amplitude, this is basically amplitude, if it will be same, then it will totally be zero. If it's not same, let's say this is a1 and this is a2, and let's say a1 is greater than a2, then we will get a wave something a3 which will be less than this. Either see, a3 will be less than a1 for sure. Okay, but we don't know whether a3 will be less than a2 or not. It depends. So these two are basically constructive and destructive interference.
So you are saying for destructive interference,
Mhm.
both the wave will be on, the phase will be, amplitude will be same, but the
No,
phase
no,
will
no.
be
Yeah, see, what for simplicity, what I have taken is,
mm,
I have taken same phase.
mm,
Sorry, I have taken opposite phase but different amplitude. If the amplitude will be same and the phases will be
mm,
totally opposite, then it will negate each other. That it will be zero totally, right? This two wave will cancel out.
mm.
But if there will be, if one of the amplitude of one wave will be little bit more than the other, then there will be some leftover will be there in the resultant uh, wave.
So is there any number for the amplitude change between the
Yeah,
two waves?
that, yes, that you can do. It's a vectorial addition. You might have learned in mathematics the way
Mm,
you do vector addition. Not simply you will add up like 1 plus 2 3, not like that. It will be like this, waves will be given where y1 plus y2. Okay, so this is sine 1 a2 sine omega x. So how this sine functions are, it's like sine c plus sine d, right?
mm,
So 2 sine c plus d by 2 into sine c minus d by 2, sorry, cos c minus d by 2, like that, normal trigonometry. So this way it will be added, not directly it will be added. So yeah, you got my point, right?
mm, mm.
Hmm.
Yes, yes.
So yeah, where okay, so I was explaining Abbe's criteria.
Actually, last conclusion during
Hmm.
that class he said कि if the amplitudes of the waves are the same and the velocity phase shifted to lambda by 2,
Lambda
the
2,
wave
okay.
is eliminated. So
Yeah,
could you just draw and make me understand the statement?
see, what he was trying to say, the phase is basically totally opposite what you have told. That is totally telling that the phase is opposite. Let's say this amplitude, this is 10. Okay, I will give some value to this 10 something, because as a sinusoidal wave it will be having some sine omega x, it will be same. And
Mm,
I have a opposite wave here having minus 10 sine omega x. This, the phase, how this is coming, see, sine of minus x is minus sine x, right? So
mm,
phase is coming inside this, right? It might be
Mm.
kx, see, I'm messing up the units now, but try to understand. Let's say inside sine kx minus omega t. Okay, so here the phase is remaining. So if you are telling it's having opposite phase, then there will be a minus sign here which can come out, and it will be shown in the amplitude. So here if I will add it up, let's say this is also 10 sine omega x, this will be having, let's say, minus 10 sine omega x, this will be minus 10 sine omega x, and this will be just a second. This will be plus 10 sine omega x. And when this will be added, because this one will be added with this one will be added with this one, and this one will cancel out this one, and this one will cancel out this one. So net resultant will be, okay. Then other explaining Abbe's criterion for lenses to form an image, at least two diffracted beams should enter the objective lens here, and should allow to combine to form the image plane. And this Abbas criterion basically gives rise to resolution of our uh, it tells us about the resolution, and the Abbott diffraction limit determines the spot size to which a light beam can be focused. And uh, from this Abbott criterion, it is possible to uh, get the resolving power, which is given as lambda by 2 n, where n is the numerical aperture and lambda is the wavelength. And then he explained about the Rayleigh criterion, where as we know, like, to distinguish 2 points, uh, for our eye to distinguish 2 points, it has to be at a certain distance. After that only we will be able to resolve it, right? So this is given by d equals to 0.61 lambda by beta. So here beta is the numerical aperture. Yeah, this d is the distance between two minimum distance between 2 points. Okay, then he explained about the numerical aperture, and which is associated with a
Yes,
limit of
again. Hello.
yes,
Again,
yes,
again, again, again have come now. In
uh-huh.
that class, he told he in Rayleigh stated that if the maximum from one source lies over the first minimum from the other source, then the
Yes.
overall intensity profile. So, could you please draw and let me understand this again?
Yeah, that I'll explain. There, it's there in further slides. Like, that's the
Okay.
limit of resolution. Like what you told, if the max minima of one of the wave coincides with the maxima of the other one, then there we start resolving those 2 points. Okay, that I will explain it later. Okay,
Okay.
so
Okay.
then. So numerical aperture, which is defined as light capturing power of compound lenses, which we have, and there he explained about the limit of resolution, which he given as lambda by 2 sine alpha, and here from here only we can get the relation with numerical aperture also, like lambda can be, if we are considering different refractive indices, then it is related as lambda by n. It becomes 2 lambda by 2 n sine alpha, which is given as lambda by 2 n. So so this then he explained something about defects which he didn't complete, and yeah, which will be continued in subsequent lectures. So let's jump into the questions, and from whatever theories which we have recollected, from there itself we'll be able to solve most of the questions. So first question, like what should be the wavelength of probing radiation for imaging? So from yeah, so probing radiation, first, anyone want to try, like what will be the answer? Like probing radiation should be greater than the feature to be studied, or probing radiation should be same order of the feature, or probing radius will be smaller than the feature. Like what this question mean is, like whatever our material is given, okay, so what type of light we should be using, so it should be same order to that of the feature to be studied. Okay, so next question, like according to the rule of ray tracing, which of the following is correct? So ray tracing, as we have already studied earlier, uh, what different rules, like let's say our lenses are given. Okay, we have focal length 2f, back focal length 2f. So if an image is beyond 2f, then what are the rules? Like if the ray will be passing parallel to the optical axis, then it will pass through the f and it will go. If it will go directly through the optical axis, it will pass undeviated. And if the ray will be passing through the focal point, then it will pass parallel to the optical axis. So if, sorry, I did a mistake. Huh. So if the object is beyond 2f, then the image should form between f and 2f, and if the object is between 2f and f, then the image will form beyond 2f. If the object is at 2f, then the image will also form at 2f. And if the object is within the focal distance, then we get a virtual image. Okay, so here what the question says, according to rules of ray tracing, which of the following statement is correct? Okay, correct. So a ray passing through the front, a ray passing through the front focal point will be retracted towards the rear focal point. A light ray, no, it cannot. So first statement what it says is, a ray passing through front focal point will be retracted towards a rear focal point. So it's not possible. Like it's saying, if it's passing through the rear focal point, it will pass through the. This is the front focal point. This is the front focal point, and the rear focal point or back focal point. We will say it's saying this way. No, it will not. The light ray will not move like this. Okay, the light ray passing through the center will be retracted towards the focal point. No, because if the light ray pass to the center, it will directly go through. If the light ray parallel with optic axis, after detection will pass to the real focal point. So this is the correct answer. If it will pass parallel to the optic axis, then it will pass through the focal point. So this, as I have already told, like magnification, this is the magnification holds for compound. This for a compound lens, what type of magnification this is. So as I have already told you, for real image, magnification was given by V by F plus 1, and this was objective lens. And virtual image, for that the magnification was given as V by F minus 1, and this was corresponding to eyepiece. So here it is only objective lens. So this magnification is observed only by the objective lens. So Rayleigh criteria, as I have already told, this RTH is 0.61 lambda by beta. What is this beta? This beta is basically the numerical aperture. Okay. So here, what? Don't know who was asking. Can you ask the question again?
One second.
Anka.
If the amplitudes of the waves are the same,
No,
okay,
this one.
not this one. The Rayleigh criteria, right?
Mhm.
So Rayleigh stated that if the maximum from one source lies over the first minimum from the other source, then the overall intensity profile exhibits a dip in a middle at about 80% IMAX.
Oh, the intensity was the that statement was basically telling the this interference of the maximum and 80% of the maximum, right?
Like if the maximum of one source it combines with the first minimum from the other source, then the overall intensity will exhibit and it will be
80% of the
80% of
maximum.
IMAX.
Okay, yeah. This that
हाँ,
statement basically correspond to this middle portion. Okay, so let me explain this one. So when let's say 2 points are there and they're very close enough. So when they're very
could you
close enough,
draw
yes,
that waveform and then make me understand it, because in
wave
that
for.
I'm not getting the point. What will be the
Okay, I'm
first
going
minimum?
sequentially. Yes, I'm going sequentially now. Right. Uh, when see in this case, what we want is we got 2 points and we want to resolve it, right? So it is telling for each point we are getting one diffraction pattern. Okay, so if the 2 points are too close enough, then the diffraction pattern are basically overlapping. Okay, so we won't be able to differentiate it. Your question, like you are telling, the first, let's say this is the diffraction pattern for first point and this is second point. So what it is telling is in this case the
The maximum of first source will be overlapping the first minimum of second source.
this is the maximum. Okay,
Mm,
maximum of
mm,
first, and
mm.
this is the minimum of second, right? These are overlapping. This is
It is
what
also
it's.
the maximum. Is it minimum of the second? It is not the minimum, right?
Okay, sorry,
From the
uh,
second wave.
minimum of second, right? mm,
Uh-huh.
uh, yeah, minimum, right? This is the minimum.
Mm, mm.
Yeah, this is what you asked me, right?
Yes.
So maxima of first one intersecting with the minima of the second wave. So
And the
when
resultant will be,
and the
sorry.
resultant will be the as addition we will write the equation, wave equation for both of them, and yeah, those will be like in terms of science, like I have already explained, something, it will be something like that. Okay, A1, something like that, and you will just add it up, and its amplitude will be having some value. uh, yeah, it will be added as a vector quantities, not a simple addition, right? As I have already told, the
Okay.
way you do uh, trigonometric calculation. See, here one angle is there. Let's will change it little bit. Hmm, okay, and there is no time dependence. Let's will keep kx1, kx2. So this is C, this is D. So kx1 plus kx2 by 2 times sine kx1 minus kx2 by 2 cos, sorry. Yeah. mm, and what about the amplitude will be 2a1 a2. Yeah, this kind of stuff you will get if you will consider the wave equations. Got it?
Okay. Okay.
Hmm. Then yeah, to explain that phenomena further, I have taken another example for that. The primary mirror of the orbiting Hubble Space Telescope has a diameter of 2.4 meter. Being in orbit, this telescope avoids degrading effects of atmospheric distortion on its resolution. So first question is, what is the angle between two just resolvable point light sources? So again, just resolving, so we'll directly use the Rayleigh criteria. Theta equals to 1.22 lambda by d. Here our wavelength, light wavelength is taken as 550 nanometer, so we'll put lambda as 550 nanometer, and diameter of the lens which is used is 2.4 meter. So you plug it in, you will find uh, resolvable angle will be around 2.8 into 10 to the minus 7 radian. So next question, if two stars are at 2 million light year distance of some Andromeda galaxy, how close together can they be and still be resolved? So to resolve such kind of thing, like uh, common formula used is S equals to R theta for angle, like you are at a distance and you are subtending an angle theta and you are covering a distance R. So basically you are covering this distance. So this 2 point, so the answer will be like how close it will be. So it will be r times theta. What is r here? It is given 2 million light years. Two star at a distance of 2 million light year times whatever resolution which we get. So they can be around 0.56 light year far apart from each other, and they can still be resolved. Okay. So yeah, so there is another very nice concept considering this Rayleigh criterion. Uh, this we have already seen in our when we go and check our eyes. uh, they used to give us this kind of thing and tell us what to read, right? So what does this thing means? So for a normal vision to be characterized, this 20 by 20 is considered as a normal vision, okay? And every letter from here, is the sizes are depending on the size of this E, and this big E is standardized and given as 88. Sorry, how long I have been disconnected? Am I audible? Hello?
Audible.
Okay. Oh.
Audible, sir.
Hmm. So with this, uh, this E on the chart has a standard height of 88 mm, and other letters are scaled accordingly with this E. So if one has to see what this 20 by 20, 20 by 40 represent, so the doctor used to tell us to read this thing. So if we will be able to read this 20 by 40, then this signifies that we will be able to resolve the letters 20, 20. This is basically 2 rows up from the normal vision, and if we'll able to read this one, this is 2 rows below the. So what does this mean actually? This means that if we can see this one and not this 20 by 20, then with respect to a normal person can see this thing at a distance of 40 feet, with respect to a person which is having some problem, okay? So this is basically at a distance of 20 feet you used to see it perfectly. And what does this 20 by 200 means? If we want with some aid or help, we will be able to see this. So doctor recommend uh, this value to be legally blinded. That person is legally blinded if he cannot see this big value. So what are the factors which limit the resolution of this human vision? As discussed in the text also, like limit of resolution is this diffraction is always told as the limit of resolution. So if we'll do a simple calculation to see what a resolution one human eye can achieve, so from simple like single slit experiment, what uh, we have seen. So I just want to show you what values one now human vision can see, like resolve. So here, as this E value is 88 millimeter, so if we are considering this letter, how what should be its dimension? It should be around 8.8, right? Because it's zero point 0.1 times of this. So So what Rayleigh criterion tells us? (1.22 lambda by d), and here lambda will be, let's say, our human eyes is given, the diameter of iris of human eye is given as 5 millimeter. So 5 millimeter will put here. So for 20 by 20, which is considered as normal eyesight, the resolution limit for most people, resolution limit for most people is given as 5 into 10 to the minus 4 radian. And for acute vision, like, so this limit one human eye can go to resolve 2 points. So this is just one of the flavor which I want to give as a practical example of resolving power given by the Rayleigh criterion. So hope you understood. So this next question: human red blood cell measures 3 micrometer by 8 micrometer. Is it possible to view in a light microscope? Yes. Why? In the class, sir has already shown the resolving power of light microscope is around 100 nanometer, so it can easily resolve this 3 by 8 micrometer size human red blood cell. So when a layer of cedar wood oil used instead of air, then resolution of lens will be decreases, increases, remains the same, all of the above. So in class, sir has explained whenever uh, there will be any medium used instead of air and the refractive index having more than what air has, one. So what it does, it helps in accumulation of more light, so that helps in increasing the resolution. So here the answer will be increases. So when a layer of cedar wood oil which refractive index is 1.5, which is more than air, so that will basically increase the amount of light falling on the aperture. This basically increases the numerical aperture for which the resolution increases. So yeah, this is the reason. So lens defects which can be rectified by using a convergence and divergence lens with different refractive index is this has like two type of lenses are used, and this defect, this this type of rectification is done to rectify the spherical aberration. So what are these defects are basically this spherical aberration is coming because of the spherical nature of the lens. So because of the spherical nature, you can see the light passing through at different point will form different focuses, for which there is a error coming. So to rectify this error, this convergence and divergence lenses are used. And what is this astigmatism? Astigmatism is basically can be corrected by using a cylindrical lens, and because of having different lens curvature, this problem happens. And this chromatic aberration happens because of different light colors, and this can easily be avoided by using a monochromator. And coma, this can be easily rectified by bending the lens which by bending the lens basically it can partially reduce. We can use a combination of symmetric lenses, which will help to rectify this defect. So next question, identify the correct statement which depicts the relation between E and lambda. So E increases when lambda increases, E increases when lambda decreases, no such correlation between E and lambda. So we already know that common relation between E and lambda is E equals to SC by lambda. So they are inversely related. So if we'll increase D, then lambda decreases. So answer will be this one. So which of the following is not correct? Speed of light will change when passing from one medium to another and is called Snell's law. Yeah, that is correct. The statement is correct. When light passing from high density medium to low density medium, its velocity will increase. When light passing from high density medium to low density medium, the velocity decreases. This is incorrect. Uh, okay, so where this coming from? Sine I by sine R equals to n2 by n1 equals to b1 by b2. Okay, for high density, from when it has high density, the velocity should be less, and when it is low density, it should be high. Okay, so which of the following has highest resolution? From the figure itself we can see human eye has a resolution of 100, it can resolve of 100 micrometer. Light microscope can resolve up to 100 nanometer, and we're not talking about electron microscope now, which can resolve zero point 0.1 nanometer even. So optical microscope is the answer, which will be having highest resolution. Okay, and its resolution is around 0.1 micrometer. The range of position for an object in which image sharpness doesn't change is called, it's basically depth of field. What does it mean? Like, if this question means like if we're changing the position of the object, after that also the image, it's still not blurry. Actually, there's a range of object position we have for which the sharpness of image still remains. Range of object position, and this is basically explained as depth of field. So best possible resolution of optical microscope, I've already explained this. So this is basically 3.1 micrometer. The human eye is like a camera, and hence it contains a system of lenses. The eye lens forms. The human eye always forms an inverted image and a real image of the object on the retina. Which of the combination is well suited for the following statement? Upright and smaller image is created by a concave lens. So concave lens will consider, then it always gives us an upright image. Okay, if this is a object, this is the image. Upright and smaller image is created by a concave lens. Yes, that's true. Inverted and larger image is created by concave lens. No. Depth of field is a key factor when selecting a microscope to examine fractured specimen. That's true. Like if a specimen is given which is having lots of ups and downs, then depth of field matters a lot, because the image can be made uh, focused by varying the distance of the object. Okay, so this is a key parameter for fracture specimens. So contrast is a key factor when selecting a microscope to examine the fracture. No, because it will be very difficult to uh, do a contrast for fracture specimen, because it will be having a lot of ups and downs. So it's difficult to get a good contrast for that. So answer is first one true, second one false, third one true, fourth one false. So if the ocular of a microscope is having a magnification of 5x and the objective is set at 10x, what is the total magnification of the microscope? So as we know, magnification will be given as product of 2. So here it's basically 5x times 10x will be 50x. A stainless steel sample with lot of bits, a light microscope which uses 500 nanometer wavelength, monochromatic source and constant numerical aperture, which of the following condition will have better focus of the feature? So here, as we have already told, like whenever we put a medium in between our objective lens and the source emanating the light, then whatever material it will pick here of diffraction index greater than 1, then that will increase the chance of more light to increase the reception of more light. So what it does is it increases the numerical aperture and eventually the resolution. So whoever of this material will be having more refractive index, and that will be focusing better. So here this paraffin oil is having refractive index value from 1 to 1.4. This methylene iodide is having 1.75, and this cedar oil, which we have already seen previously, 1.2 or 1.5. So this methylene iodide is having the highest refractive index, for which this condition will be giving us a better focus of the feature. Okay, so having highest refractive index. So again, this one I have already explained. The from lenses equation, which is given as 1 by f equals to 1 by u plus 1 by v. From here, using the equation of magnification, which is v by u, we can equate this, and for eyepiece we get the equation for magnification as m by v plus 1. So here magnification in a compound lens is observed by only eyepiece. And what will be for objective lens? Again, for objective lens it is v by f minus 1. Which of the choices will give you the best resolution of small objects? Anyone want to try this one? I can give you hint for which you can guess, the help of which you can guess. Like here magnification is given, so for best resolution we need good magnification. And apart from that, what else we have given? We given a numerical aperture. So here, like oil, as I have already told, we are adding extra material having a different refractive index which help in capturing more light, for which the numerical aperture increases and we get a better resolution. So here the answer will be 50x oil, numerical aperture highest 1.4. Now this will give us the best resolution. So again, to recollect how resolution depends on best resolution given by material with more numerical aperture. And this condition is provided by any material. Here oil we are giving, so this is the medium which is helping in increasing the numerical aperture by allowing more light to pass through. Next question, as the spacing in grating increases, the distance between the corresponding diffraction spot. So this is very nicely explained in the lecture itself. So as the diffraction grating increases, the corresponding diffraction spot decreases. Here from the lecture itself I have taken like the pattern from grating with spacing 0.125. We can see, okay, so closely spaced with least uh, grating size. So with spacing, when we have 100 mesh grit with spacing 0.25 millimeter, it is little bit better than this one. So as the spacing in grating is increasing, the distance between diffraction spot is decreasing. Okay. So again, same question. When a layer of almond oil used instead of air, what will be the resolution? Anyone want to answer? So what does resolution depends on? The numerical aperture, and how the numerical aperture is increasing. Yeah, increases. Thank you. The same logic goes. having more refractive index. So more refractive index, the better is the numerical aperture is higher, and it allows more light, for which the resolution increases. So which among the following light is suitable for getting a better resolution? Anyone want to answer? Which one? Like how resolution depends on the wavelength? Basically, resolution is inversely proportional to the wavelength. So better resolution means lower wavelength, right? Yeah, sure. I will share all these questions in PDF. Actually, this will be shared in YouTube also. You will be getting the links for that, and you can see all the answers, and you can see the explanations there too. So yeah, for better resolution, we did a lower wavelength. So here blue is the answer, because blue is having the least wavelength among this. The easiest way, with Q we know the wavelength increases here. It is red is having highest wavelength, blue least of them all. The resolution is the ability of a lens to distinguish between small objects close together. What approximate resolution can be obtained with a lower power objective lens? Assume the wavelength of light is 500 nanometer. Anyone want to try and tell me answer? So how resolution is given? D equals to, here what are the values given? Na is given, so lambda by 2Na, right? Lambda is 500 nanometer. So 500 nanometer, which is equals to 500 into 10 to the power minus 3 microns, right? So what will be the answer? 0.5 microns, correct? The answer will be 0.5 microns. So next, what is the unit of brightness in electron microscope? As I have already explained, it is ampere per meter square stereo. Anyway, sorry, area. Uh, all the I have mostly discussed all the questions now. Now, like, anyone want to ask anything? I will try to answer that. There are certain things, like there are certain confusions people always used to have, like between STM and STEM. This is a little bit of introduction to that, like to go into the course itself, like TM first. transmission electron microscopy. Here in this type of microscopy we used to see the light passing through the object itself, and then we see it. STM, TM and STM kind of same, but STM has better interpretability than TM. So in certain circumstances we prefer STEM over TEM, where STEM is here scanning transmission electron microscopy. Here in future you will be reading a lot about this, but I'm just introducing it. This HADAF, high angle annular dark field, this is basically a detector used in TEM to detect the electrons. STM is scanning tunneling microscopy. It is a bit different from this type of microscopy which is mentioned. Why I have mentioned this? Because people get confused between STEM and STM. So TEM is basically parallel illumination of electrons. Detectors are not required here, and image formation is through objective lens and projected onto the screen through a projector lens. So here contrast generated are either diffraction contrast or phase contrast, which you will be reading in the future. And STM converged probe of electrons scan the sample and image forms through scattered electrons. Here the important thing which you will be learning in future is here Z contrast is used, and here diffraction contrast or phase contrast is used in TEM. This is the only this is one of the difference between TEM and STEM, and that's why because of this interpretability, STEM is sometimes preferred over TEM. So this is, you may say, significance over TEM. So to introduce this course into this topics, this is another question for that. So in context of scanning electron microscopy, we need to find out what information gathered by what type of electrons. So in scanning electron microscopy and transmission electron microscopy, here the images are taken after passing through the sample, but here when it is reflected the images are taken. So basically you may say the source of light and the detection of light are at the same position, but in TEM the source and detector detection are opposite direction. So yeah, but there are a lot of electrons which comes out while performing this scanning electron microscopy. So this secondary electrons, what does this help in? This help in failure analysis of fracture surfaces. Backscattered electrons, this helps in distinguishing chemical distinct phases. Characteristic X-rays, this helps in chemical finding out the chemical composition analysis. And this diffracted backscattered electrons, this helps in crystallographic or finding out the crystallographic orientation of grids. So yeah, this is it. So any doubt which you have, you can ask, or anyone has any doubt. Okay then, you guys can leave. Whoever I'll be here for some time, and whoever will be have doubt, I will be clearing it. Thank you so much. Thank you, Lucas. Yeah, I will share that. I think as you have registered it at that portal, they will be sharing all the links for YouTube channel, PDFs, and everything. There, there you will get everything.
Sir, can you go your previous slide?
This one, previous, last, the question slides or
Yeah, last one. Yes, sir, last one.
here last question. This one.
No, sir, that column and which was match.
Acha, acha, matching. Okay.
Yes, sir. Sir, there is no that secondary electronics. So how they are detecting the a failure analysis of fractured surfaces.
See,
So
yeah,
actually, we are
this.
using the fractography
Okay.
to analyze.
Yes.
So fractography we are using to analyze the fractured surfaces of any material to detect the cracks or it is that grain structure. So that defines the actual fractured surfaces on that surface.
Okay.
So so where these secondary electrons are using to.
See, as you will learn in future in SCM course, these different electrons will be having different energies. Okay,
Okay,
so
sir.
accordingly they will be able to determine what type of information we want. So when you say uh, to analyze this failure of fracture surfaces, uh, when the electrons will be facing there, let's say low line, the low energy electrons, they'll be facing this uh, surfaces, different height surfaces, and accordingly they will be leaving the surfaces, right? So this is basically, you may say, this is taking the surface topography, like it's mapping the surface and taking the information from the surface. Okay, so one concept you will learn, it will be
Yes.
penetration depth. Okay,
Okay.
that that will tell you what type of electron will give you what type of information. This fracture surfaces, this is basically topographic information. Okay, so this
So
information, yes.
suppose sir we are using this penetration defect to see the depth of
Okay.
gear cutting like worm gears or
Hmm.
bevel gears.
Hmm.
So for that these secondary electronics how they are using to determine the fracture analysis of that T structures if they are matching with two together. By
What
that
it
there will
will
be also friction will be also there. So by that,
this electron will be having very less energy. So yeah, this is little bit of destructive, but it depends on what type of material we are using. Okay, so if the material will be giving charging effect, lot of charging effect, then we don't
should be
normally
applicable for.
prefer this method if it will be giving lot of charging effect, because it will damage the material. But if the material is robust, so we for sure we can use it, like it will not get damaged because of this charging effect, right? So again, you can use multiple characterization technique to characterize different phenomena, like for let's say fracture surfaces. Only if you want information of the surface only, then you can also do AFM, right? Atomic force microscopy. That will also give you the surface information, like SEM. So yeah, it depends on what is your motive and what material you are using, and accordingly you have to choose the characterization technique, right?
Yes, sir.
Hmm.
So, sir, there is any limit, like we have to determine the mechanical properties like hardness. So for that, we should know that it is how much like diamond. We have the diamond which has the highest hardness. So for that, we cannot use secondary electrons.
No, for hardness you have Victor's method, right? Victor's hardness calculation, something like that. For ceramic it is used, right? uh,
Yes, sir.
yeah, so that method you can use, but this one you cannot use for detecting the hardness. Hmm.
No, I'm saying, sir, for that material which have high hardness,
Mm, I didn't get your point. For that
like
material,
sir, we choose one material and we can add reinforcement or any ceramic so that we make a metal matrix composite.
okay.
So for that, when we will see go for its testing, like non-destructive testing, to
Hmm.
detect the tensile test, this fracture test, compressor test. So for that, how can we analyze that these fracture analysis of that by secondary electronics?
Secondary, I think for testing those things, I don't think secondary electron will help you that much. For that, I think you said non-destructive, but it's very difficult to give one solution suggestion for non-destructive one, because UTM, which you have heard, right?
Yeah, universal testing machine. Yes, sir.
Yes, that one is used for measuring those kind of things. But again, what I have seen, that is little bit destructive too. Like if like eventually it will break your sample, because it will test your sample to its limit. So if you are looking for uh, stress strain measurement, so I don't think SEM will help you, because it's as you have known, like that will only give you surface information, or what type of elements are there. This type of information you will only get. So only mechanical characterization you have to do. You have to look for different methods. Vickers hardness method, and yeah, UTM for stress strain. Yeah, different methods are there. Yes.
Okay, sir. Thank you.
Thank you.
Sir, can you share these questions in PDF, sir?
Yeah, sure. I will be sharing this, because in the site itself they will be sharing all the YouTube video links and PDFs. All will be shared there. So yeah, you can check the website there. Yeah, it will be uploaded within a week.
Okay, sir. Thank you.
Thank you.
Okay.
Yes, you want to ask something? Do you have any doubt? You can ask. I can go through the answers again if you wish. Okay, sure. I want questions itself on the one. Okay, you want
No,
me to
sir.
all the questions, right? From here, this is one question.
Yes, sir. From first question itself, sir.
This is okay.
Yes, sir. The, then next, sir.
Mhm.
Next question, sir. Next, sir.
Okay, this one different. Yeah, this one.
Yes, sir. Fifth question, sir. Because I am not attend first 8 questions, sir. 10 questions, sir. After only I was attend, sir.
Okay, no problem.
Sorry, sir. No.
No problem.
Okay, sir. Next question, sir. Sixth. Yes, sir. Seventh, sir.
Okay. If you are going through the
Yes, sir.
questions, if you are going
Yes,
through the
sir.
question, you can just. I can tell you some points so that it will just stick to your brain. Like it will help you
Okay, sir.
later. Like let's
Okay,
say.
sir.
Here. First question. Let's say what should be the wavelength of probing radiation for imaging? uh,
Yes.
what type of wavelength we want, like let's say we want to see a smaller object, so for that what type of wavelength we need comparable to the size of the smaller object, or if you want little bit bigger than that 10 nanometer, if you want bigger than that 1 meter, accordingly we change our wavelength. So here the second option tells that like probing radiation should be of same order to that of
Yeah.
feature to be studied. What type of material
Okay.
we want, accordingly
Okay,
that
sir.
type of wavelength we will choose. This question's answer, just this is the justification for that answer. The first
Oh,
second one,
okay, sir.
this one's telling according to the rules of ray tracing. Okay, so uh,
Okay, sir.
when a lens is given, okay, so how the rays basically goes pass when we draw a ray parallel to the optical axis, which you can see here. If it is
Yes,
parallel
sir.
to the optical axis,
Yes,
just
sir.
a second.
Okay.
Mhm. When it's parallel to the optical axis, then after passing through the lens, it will always pass through the focus. Okay, this is one of the
Yes, sir.
rules. So
Yes,
then
sir.
another rule is when the ray is passing through the center of the lens through the
Mental.
optical axis, it will pass as it is. It will not deviate. And when it
Okay,
is
sir.
passing through the focus and then through the lens, then it will pass parallel to the optical axis. What is this optical axis? This optical axis is basically passing through the center of the lens. Okay,
Okay. Okay.
so from these options, the first option tells you a ray passing through the front focal point will be
Okay.
retracted towards rear focal point.
Mental.
This one is the first focal point, front focal point, and second one is the rear focal point. So
Yes,
first
sir.
one is telling the ray is passing through the front focal point, then it is passing through the rear focal point. It's not possible because when it will pass through the front focal point, it should pass parallel. So this is incorrect.
Parallel. Sir.
Uh, the second one,
Okay, sir.
the light ray passing
Light
through the center will be retracted towards front focal point.
point.
So when it will pass through the center, it should go undeviated. So it is telling it will pass through
Yes,
the
sir.
front. It is not possible, right? It should go undeviated. So
Yes, sir.
therefore
Okay,
it is
sir.
wrong. So light ray
Um,
parallel with optic axis after
optical axis.
retraction will pass through real focal point. This is correct. When it
Yes, sir.
is
Correct, sir.
hmm,
Now I
when
understand, sir. Correct, sir.
okay. So
Okay, sir.
then next question. Next question.
Okay.
Actually during the derivation from the lenses equation. Lens equation is given 1 by f equals to 1 by v plus 1 by u. From this equation and magnification equation equals to v by u, you will solve this two equation. Then you will find two equations. One,
Yes.
m equals to v
M.
by f plus 1. One, m equals to v by f minus 1. So this m equals to v by f plus 1 is given as objective lens. M equals to v by f minus 1 is given as
IP.
eyepiece lens. These are the magnification
Yes.
for eyepiece lens and object lens. So according to this question, it should be only magnification
Yes.
for the object lens, objective lens. Okay.
Objective lens. Okay, sir.
So next question, Rayleigh criterion. This is basically tells us what is the resolution. Okay, so this one is RTH
Okay.
is 0.61 lambda by beta. Here beta is representing the numerical aperture. Okay, this
Okay,
this
sir.
this derivation you can do, but I'm not doing. It's little bit complicated.
Okay. Okay, sir. I will try.
Hmm.
Okay.
Actually, sir, in class
Next.
also, sir didn't do this derivation. Okay,
Okay, sir.
so
Okay. Next.
next question. Yeah, this one you just saw.
Okay.
Human red blood cell measures 3 micrometer by 3 micrometer. So what is it possible to see by light microscope? Obviously, because by light microscope we can go up to 100 nanometer. That is zero
100
point 0.1
micron.
micrometer we can go. It is
Oh, okay, sir.
it is quite big
I
enough
understand.
to see under light microscope. So next question. This
Sir,
from what question you have
sir,
attended?
sir, I have a doubt, sir. In assignment question,
Mm-hmm.
I faced one problem, sir. N equal to 1.5 they are given, and then another one n value they are given, that is n is equal to 1. Then thickness of this lens also given, but I can't do that problem, sir,
What was
because
the
I can't understand.
what
Sir, in
question?
assignment question, sir. Assignment question, sir.
Now, what was the question? Like what it asked for?
Oh, sir, sir, few seconds, sir. Few seconds. Few seconds, sir. Please. Yes, sir. We got it. Yes, sir. They calculate the optical plan length, path length difference, sir. Hello, sir.
I'm listening. Path length
Optical path length difference.
difference. Okay.
Difference.
Mm-hmm. You have to calculate that. You have given n
Yes, sir.
and
Given in medium 1.33, sir.
1.33. Okay.
And then thickness they are provided, sir, 1.5 micrometer.
1.5.
5 micrometer.
Okay.
And another one, the thickness where n value they are provided, sir. 1.5, that medium.
2n. One is 1.5.
Yes,
What is
sir.
1.33?
1.33 is n medium they are provided, sir. But I can't understand, sir. N medium means what? N1, N2.
Okay.
I think
N1.
that formula I must use it, sir, but I can't get that result because delta is equal to Ri minus 1 into d divided by d. That formula I have, but I can't able to get that correct answer, sir.
Can
The
you again
delta
tell
is
the
equal to n
n?
delta equal to n1 minus n2
Huh?
into t.
Okay.
One separate answer is there.
Okay. Okay. Okay.
Separate
There are
formula is
different
there. Another
answers.
one,
Okay. There are
yes,
different
sir. I got.
options. There
Yes,
are no
sir.
values are not given for that.
Oh, okay, okay, sir.
No,
But I'm confused. Which one is n1? And then finally I will get a minus negative answer.
uh,
Otherwise, it is n1 minus n2 is I think it is a difference or anything, sir. In delta is equal to n1 minus n2 into t. It is I have one formula, sir.
yes.
Yes, sir. I don't know which one is a n1 and then which one is a n2.
So see, for this optical path, what you need, like it's there in one of the slides, like it should be geometrical path divided by the refractive index, right? This one, right? Hmm?
Yes, sir. Reflective index, yes, sir.
Geometric path by refractive index. So you have to see for which one,
Okay,
uh,
sir.
for which refractive index, what will be the geometric path, and what was the question? What is the optical path length, right? Means you have to
Calculate the optical path
path length.
length difference.
Okay. So basically, you have to calculate this geometric path by refractive index for individual mediums, and after that, you have to calculate the optical path length difference.
Okay.
Because see, what you are doing, you are getting
Okay.
minus, because it will be, if refractive index is in denominator, if it will be 1 point, if you will do 1.33 minus 1.5, it will be negative, but if you will take it in denominator, it's opposite, right? In numerator
Yes,
there will be
sir.
something, yeah, so it is, this value become bigger than this. Just try it.
Yes, sir.
Just let us try it and see. Hmm.
Sir, the optical path length difference comes only in positive or negative, sir?
It has to be positive.
Oh, positive means okay, sir. Positive means the difference between N1 and N2. If I take like that, sir, the
Okay,
difference between N1 and N2.
you are telling N1 and N2 like 1.5 minus 1.33 times 1.5 you
Yes,
will
sir, yes,
take
sir.
just. So
Yes,
this
sir, yes,
one,
sir.
this is not giving you an answer.
Oh.
This is,
But two method I was done, sir. I
mhm.
got two formulas. So two method I was done, but one method I was getting 0.33 value and then another method 0.255 micron. But in this assignment question, they are provided only 0.255. So what I am confused means N1 and N2 is a difference. They are taking a difference, but I am confusing with N1 minus N2 means if I take a N1 1.33 and the N2 1.5 means I will get a
Different answer.
negative value.
Okay.
So that confusion I got. So then only I will ask you in this question, sir.
But yeah, optical path length, if you will get a negative, then what will be the interpretation for that? Like it's not like length cannot be negative, right? It's not feasible. So
Yes,
you
sir. Yes,
have
sir.
to look for an
Yes.
answer which will be
Um,
feasible, right?
Positive.
Hmm.
Okay, okay, sir. Okay, sir. Now I understand, sir. Then, sir, another one question, sir. Mm, when when the image plane is not flat but it is concave sphere surface,
When the
when the
image,
image plane is not flat,
uh,
it has concave spherical surface as
okay,
seen from objective. So this is which kind of abrasions, a spherical or curvature of field. So that much they are provided, sir. I am not understand, sir, because all of the 10 question I got answer, but this question I got I am confused a little bit that this detail also not clearly mentioned in this
lecture.
presentation, sir, in this
Hmm.
YouTube video also, sir, not mentioned clearly, sir. So I need that answer, sir.
So can you
Once again,
can you tell me the
will
question?
read that question, sir.
Hmm.
When the image plane is not flat,
Image
image
plane.
plane is
Acha,
not
acha.
flat,
Hmm.
but it has concave spherical surface
Hmm.
as seen from the objective lens.
Hmm.
So, this is which type of defect, sir? When the image plane is not flat, but the concave spherical surface is seen from the objective. So, sir, in a video, they are provided some images, sir. So that
Hmm.
images interpret, I'll conclude some answers, sir. But they are somebody told it's not a correct answer. But spherical aberration is a correct one. Somebody told, sir. But still now I am confusing, sir. Which one is the correct answer? I don't know, sir.
Okay, let me think.
Somebody told
Hmm.
spherical aberration is a correct answer.
Hmm.
But in if I taking answer curvature of field, some area I was seeing the curvature of field. Which one is correct one? I don't know, sir.
Curvature of field. Field
Field.
curvature. Yeah, basically we're telling that's distortion, right?
Yes, sir.
Distortion.
Distortion is by
Yeah,
for example,
that might be correct.
uh, curvature of field is correct, sir.
Yes.
Yes, sir. Okay, sir. Okay, sir.
Hmm.
Thank you, sir. Because somebody told spherical, it is a spherical aberration because it will present spherical surface. So that much confusion I got, sir. So then only I asked in this question, sir. Thank you, sir.
Okay.
Okay, sir. Thank you, sir.